and 5-year-old son. He served in the United States Air Force and is currently an investigator with the New York State Police. Tim is on the advisory board for the Adirondack Sky Center and started taking space pictures in 2013. His father and grandfather, also named Tim, were astronomy enthusiasts, and it was passed down to him at an early age. I expect his 5-year-old son will be the next one in line. Tim is a tester for ZWO astronomy cameras and has a lot of experience with new and upcoming astrophotography equipment. Tim enjoys imaging everything in the night sky to include asteroids, comets, galaxies, nebulas, star clusters, planets, the moon, and the sun. His favorite scope to view and image the sun with is the Lunt 152mm solar scope. He has conducted several astrophotography workshops for the Adirondack Sky Center, including a solar imaging workshop in advance of the Great American Solar Eclipse, and was featured at the observatory on the day of the eclipse event. He has also presented at the Northeast Astro Imaging Conference and on the Astro Imaging channel. To view Tim's work and learn more, check out his website, astronorth.com. So, take it away, Tim.
All right, thank you very much for that introduction. And it's my pleasure to be here. Thank you very much, Steve, for inviting me tonight. And thank you very much to your society for having me tonight. I'm very honored to be here. And at the same note, thank you very much for joining us tonight, Don. It was a pleasure meeting you at the Astro Imaging Conference down in Rockland County, and it's great to see you again here. So I'm going to get going. I just want to make sure my screen's displayed the slideshow.
Looks good.
Okay. All right, so tonight we're going to be talking about safely viewing and imaging the sun. The objectives tonight, I cannot stress enough the solar safety. Looking at and imaging the sun is risky if you don't have the correct equipment. You can damage your eyes, you can damage property, start fires. So I can't stress that enough to be careful. We're also going to talk about the features on the sun that we can view and image, the types of solar filters, solar dedicated scopes. We're going to get into focal lengths, lenses, and scopes, different tripods and mounts. And also we're going to get into solar imaging cameras and imaging the sun in the various wavelengths. White light, calcium K, and hydrogen alpha are my primary wavelengths that I image in. Then at the end, I have some stacking, sharpening, and processing to quickly go over and show how I process solar images. So a little bit more about me. I've been astro imaging from my backyard since April of 2013, but it's been passed down through my dad and my grandfather at a very early age. So I believe I was probably about 3 or 4 years old, a little bit younger than when my son started looking through the telescope, but he is very capable of running the solar scopes. He loves looking at the sun, loves looking at the computer screen when I'm set up in the backyard imaging the sun. I'm an advisory board member for the Adirondack Sky Center. We have a great astro imaging conference every fall. That's where I met Steve, and he's attended, I think, the last 4 years, and we have a great time out there. It's a 4-day workshop, and it's hands-on. I also do outreach events in my local area and also at big events that I get invited to. I enjoy sharing the sun. I have boards that I have set up with images that I took and that I show off to the public and get our youth involved and basically share the passion and share the hobby. And again, I'm going to talk a little bit more about safety. Never look or image at the sun without a proper solar filter. Over to the right, you can see this is an actual cap I used, a lens cap that I made a mistake. Even me being one of the experts that image the sun and view the sun, I mean, I made a mistake. So it's so easy for people to make mistakes. And you also want to research and double check your setup to make sure it's safe. And also inspect your filter for holes and tears and anything that's going to let the sunlight through. And when I image the sun, and in addition to other objects in the sky, I like to know a little bit about what I'm looking at. So I have some stats and some information and some facts about our sun. The most important thing that I like to pass on is the sun rotates east to west. So when you see a sunspot coming into view on the eastern limb, it's going to be rotating to the west. And so it gives me a little bit of time so I can kind of figure out where that sunspot or the solar activity is going to be to image it. And our sun, it's the composition of our sun, it's 75% hydrogen, 25% helium. And then the other elements and metals are less than 0.1%, which include oxygen, carbon, nitrogen, silicon, magnesium, neon, iron, and sulfur. And the kids love this picture that I have on my poster board. It shows the sun's diameter, which is 864,576 miles. And it also shows how small our Earth is in relation to the sun, which is 7,918 miles. And 109 Earths can fit across the diameter of our sun, which is incredible. And when we're looking up at the sun, the apparent size, it's going to be about 1/2 degree, which is the size of your pinky. If you hold it up to the night sky, just to give you an idea of that. And our solar cycle, many people are asking me, oh, well, I don't see any sunspots. There's not really a lot of activity going on. And that's because we're just coming out of solar minimum. The cycle 25 began on December 2019. So now we're starting to see a little bit more sunspots and some solar activity picking up. And there's actually been quite a few sunspots that have been passing through or rotating through on the sun that I've been out there imaging. And it's an 11-year solar cycle. And cycle 24, which was the last cycle, started December 2008, and the maximum was April 2014. So that's going to bring us to solar maximum around the Great American Eclipse that's going to transit across the US. And that's going to be interesting to see with the sunspots and the solar activity. Some of the features that we look at on the sun, in white light, we're looking at the photosphere, which is the lowest visible layer on the sun. And that's where we're going to be looking at the granules and sunspots. We also have a calcium K, which I'm going to talk about, which we look at the lower chromosphere, which has the magnetic field supergranulation cells and the sunspots. And then hydrogen alpha, which is my favorite wavelength to image, shows the upper chromosphere, the filaments, prominences, flares, the spicules, and the sunspots. And I have a little GIF that I have in the slideshow to show you some of the spicules and some of the little flare-ups from the spicules that are really wild to watch, because I'm really getting into the like putting compositions together, taking pictures and then putting them together to create little videos. And it shows some really cool activity. So we have the solar spectrum, which is a broadband. If you throw a white light filter on it, you're looking at the whole solar spectrum, but just reduced down to 0.001% of the light, which makes it more safe for our eyes and for our equipment. Just to get through, here's the different wavelengths. So Daystar makes a magnesium filter, and that's at a wavelength of 517.27. They also have a sodium quark filter that's at 589.59 nanometers. And the sodium is a pretty interesting filter to get some of that white light and to get some of that like the photosphere to image. And the white light filters, as I said before, it allows the entire width of the visible spectrum, but at a reduced amount of light. And some of this you'll see on the white light filters are the sunspots, which are cool areas on the sun's photosphere. They're caused by intense magnetic fields and the movements of the gases in the sun's interior. So that's really neat to look at, because then you can see the umbra and the penumbra surrounding that sunspot, as you can see in these white light images on the screen. And then you'll also, in white light, you'll see the granulation or the granules, which are the grainy appearance that's on the photosphere, which are caused by the convection currents of plasma within the sun's convective cells. And the granulation is produced by the tops of these convective cells. So that's what we're looking at to see the granules. And then another popular white light filter are the Herschel solar wedges. Here you have a Baader and also a Lunt solar wedge. And these are pretty neat to combine with a Baader solar continuum filter. And the solar continuum filter just narrows that white light down. Its band passes 10 nanometers. And this will give you even more like you'll be able to resolve the surface granulation cells and the detail around the sunspots. But with this Baader solar continuum filter, you must use a white light filter, such as the Baader solar film on the front. You can't use this alone. And this is my favorite wavelength, the hydrogen alpha. And here we're looking at the upper chromosphere. This is where we see the filaments, the prominences, the solar flares, the spicules, the sunspots. And this filter allows the wavelength of 656.3 nanometers. And I get this question asked all the time. Hey, I'm a deep space imager. I have a hydrogen alpha filter. It's an Astrodon 3 nanometers. Can I use that to look at the sun? And absolutely no, do not use that because that alone, it's too broad for the sunlight, and you're gonna burn your equipment, burn your eyes. Just to give you an example, when I image, I like to use 0.5 angstroms, which is 0.05 nanometers. So just to give you an idea, those night sky or hydrogen alpha filters are 3 nanometers, 3 nanometers to 12 nanometers for narrowband. I'm working with 0.05 nanometers. So just to show you, it's not safe to use your deep space hydrogen alpha filters. And these are some of the pictures, some of the features. You can see in the upper left, there's a active region that's just going to be rotating out of view on the on the eastern limb. And then you can see to the right of that picture is a filament. And the filaments are prominences, but they're not viewed on profile because they're head on with us. And the prominences are clouds of gases and plasma from the chromosphere, which orient themselves along the magnetic lines from the solar sunspot pairs. And they can move, they can extend more than 30,000 miles above the sun's surface, and they can also cause the coronal mass ejections. And then the spicules, which you can see, let's see, on the coronal loop, which the bottom right image, you can see to the left or above and below the loop, there's kind of on the limb, there's those little jets. Those are the spicules. And those are jets of dense gas that are ejected from the chromosphere. And a couple more. There's a couple active regions in hydrogen alpha. And that's why I really enjoy imaging in hydrogen alpha, because I can go out one day and then the next day and the active region looks totally different. There's something new. There's something more dynamic to image on the sun. And then here's what I was talking about, the time lapse. Just putting a couple hydrogen alpha videos of the prominences together, and you can see the spicules jumping around. You can see some of the plasma from the prominences moving. And this is relatively short. This is about let's see. So I took a minute video every 5 minutes and composed it for about an hour. So there's quite a bit of movement in a short amount of time. And then with hydrogen alpha filters, you can double stack, and that narrows the bandpass to bring out more detail and contrast on the sun's disk. So the Lunt scopes, they have the external double stack echelon, which is on the front, and then they also have an internal. So my Lunt 152, which is on the left, has that internal pressure tuner. So to double stack that, I combine it. And then on my Lunt 60, which is on the right, it's a front mounted echelon, and it adjusts the tilt. So it's not pressure. It has the single stack is pressure tuned on the 60, but the double stack is tilt tuned. And then to get into your entry-level solar scopes, I started back in 2013 with a Coronado PST. It was a great scope to learn on. I actually did a couple modifications to it just so I could start imaging with the high-speed web cameras back then, before I got into the ZWO cameras. And I also used DSLRs on it. And so the entry-level PST, it's a 40mm aperture scope, and it's $699. And it is tilt tuned, and without double stack, it's 1 angstrom. And then when you double stack it, it brings it down to 0.5 angstroms. And these are some images that I captured with the PST back in 2014. And you can see back in 2014, there was a lot more solar activity on the sun than there is now. And then the LUNT 50, the LUNT LS50 and the LUNT LS60. I had both of these. I actually just sold the LUNT 50 recently. It's a great scope, but I just didn't use it as much. But it's a great entry level scope. It has a helical focuser on it, and the bandpass on that is about 0.7 angstroms, and it's pressure tuned, and it starts at $849. The nice thing about the LUNT scopes is that you can put them on your scope. You don't need power. So my LUNT 50, I had it on a nice compact tripod, and I could throw it in a backpack and hike with it, bring it to the park, and show kids the sun with it. With the LUNT 60, the LUNT LS60, it has a B1200 blocking filter, and it's also 0.7 angstroms. And it comes in a tilt tune version, which is a little bit cheaper than the pressure tune version. But if you're getting into imaging, then I would highly recommend the pressure tune version. But if you're looking for a visual, the tilt tune version will work just fine for you. I like the pressure tune version because it gives you a nice even disc, and there's nothing that beats a LUNT full disc image, in my opinion. And these are just some collection of some hydrogen alpha images, and it shows what scope I use to take the images over the years. Coronado PST, and then the LUNT 60s in the upper right. And then Daystar just came out recently with the Solar Scout. I had it at NEAF 2 years ago out in the solar field, and that was a phenomenal scope to play with. It does require power because it heats up mica inside it to come on band. But the nice thing about that is once you realize where the tuning position has to be, so mine was 12 o'clock, it would come on band every time, but it takes about 15 minutes to warm up and heat up. The Daystar Solar Scout, the DS model, has a very narrow bandpass at approximately 0.5 angstroms. So the views through that were pretty sharp. But as I said before, it requires a small portable power pack to heat it up, and it takes about 15 minutes. Then the Daystar Quark. This is a popular eyepiece filter that's been around. It's popular because people who use refractors can just put this right in their diagonal. It has a built-in 4.2x Barlow, and they can image the sun with their nighttime refractor scopes. So I use this. I have used it on my LUNT 152, and that's pushing the limit for the energy rejection filter. But when you're using it on a refractor 80mm or less, Daystar says you don't need an energy rejection filter. An energy rejection filter is something as simple as a Baader UV-IR cut filter. And then on that note, the UV-IR filter alone is not sufficient for viewing the sun or imaging because obviously it's letting the full spectrum of light through, which could burn your eyes, will burn your eyes and burn equipment and start fires. And then if you're over 150 millimeters, Daystar says to use a front-mounted energy rejection filter, and this will block the harmful UV and IR wavelengths. And this is recommended for the larger aperture refractors and SCT scopes. And again, the front mounted energy rejection filter is not sufficient for solar viewing or imaging alone. And then the calcium K filter, Daystar has a calcium H quark, and that is a little bit more higher on the spectrum, so it's easier to view. I like the calcium K filter because it's at a wavelength lower on the solar on the continuum, and it's also going to be more sharper, in my opinion, just because it has the lower chromosphere, the magnetic fields, the supergranulation cells, and the sunspots. And a lot of people, when I set the scope up on doing outreach, I link this scope to my computer to show a live view, just because a majority of people who try to view it through an eyepiece, all they see is a blue hazy ball that appears kind of blurry and out of focus. But some of the older people who had cataract surgery can see the calcium K, see through the filter perfect, and see the actual, it looks like the cracks on the sun, as I call them. But it's really appealing to if you can view that. So that's one of my favorite spectrums to image, just because you see a lot of the sunspots and the lot of the supergranulation cells. So it's a really cool wavelength. And here's a couple images. The large full disk on the right is from the NEAF Solar Star Party back on April 22nd, 2018. And we had a nice sunspot to look at back then. And then tripods and mounts. You can either mount your solar scope on a fixed tripod, or you can put it on a motorized mount. Because the Earth rotates 360 degrees every 24 hours, the sun drifts west 15 arc seconds per second, which is the equivalent of its own diameter every 2 minutes. So if you're using a higher focal length telescope or solar scope to image the sun, you're going to notice that it's drifting quickly. So then you're going to really want to use a motorized mount that can track the sun. And then a lot of people ask me, how do I polar align my mount during the daytime? So if you don't have your mount on a pier, or it's not set up from the previous night with a nice polar alignment with Polaris, I use my compass, and then I use the offset for magnetic declination. And then that will get me from magnetic north to polar north. And then if I'm set up for a while, what I will do is drift align to align the sun in the scope. And then once I'm drift aligned, I can stay on the sun all day until I have to do a meridian flip, or if somebody moves the eyepiece a little, then I just move it back into view. And here you can see the difference between magnetic north and polar north. For me in Plattsburgh, New York, it's negative 15 degrees. So it offsets it quite a bit. And here's the magnetic declination map. And another difficult part of viewing and imaging the sun is actually finding the sun. As easy as it sounds, that's one of the most difficult parts of imaging the sun, especially with a Daystar quark or a higher focal length scope. So they have the TeleVue Sol Searcher, the Coronado Sol Ranger, the Heliopod Sun Finder, or the Daystar Solar Bullet. Those are the basic sun finders that are on the different scopes. And on the images, you can see on the bottom left, I have my Lunt scope with the TeleVue Sol Searcher. And then in the middle, the Daystar Solar Scout with the bullet. And then on the right-hand side is the PST, which has the little white light in this, or white circle in the center of the finder. That's how you align the sun on those. Okay. And then once you're on the sun, another solution is to use the Astrospheric Hino's solar guider. And this I absolutely love. I don't know if some people have seen me set up with it, but all I do is point my mount to roughly polar north, and then I calibrate on the sun, and it will stay on the sun all day long. And if somebody pulls on the eyepiece or somebody moves it, it'll center the sun right back where it was. It's really wild. and it's a standalone unit, so you don't even need a PC required. You just need a power source. And then another challenge when you're viewing or imaging the sun, you have the sun's glare. So what I use on the left-hand side, you can see my son in my SkyShed pod, and we're viewing the sun on the computer screen, and we have it outside of the sun's glare. On the bottom, I have some solar Telegizmo solar covers to keep the sun from shining on the screen. I also use it as a hood to view the sun, because you get the sharper resolution or the sharper views when you have the sun's glares blocked from the eyepiece. And on the right hand side, I have a box that I use just to keep when I'm doing outreach, and that way people can see the screen and it's not interfering with the sun's glare. And then focusing on the sun, on the solar scopes, it's best to use a 2-speed focuser, just because when you're at a higher focal length on the sun, it's easier to have the fine motor control when you're rocking your finger to find that critical focus. With a single speed focuser, it's more sensitive, so it jumps around a bit more. And I've moved up to, I have a ZWO EAF on my solar scopes. It's electronic autofocuser. I'm not using it as an autofocuser, but I'm using it as an electronic focuser with a hand control. So when I adjust the focus, it's not jumping around on the sun. And now I'm going to talk a little bit about imaging the sun, and we have to start somewhere. So I've seen some people who have been their first solar images. Now that there's newer technology out there, they just blow me away for their first images. But these are my first images from May 2nd, 2013. And I used the Coronado PST and a Canon 450D DSLR. I still remember this day when I took these images of the sun, and I was able to basically bring it into Photoshop and adjust the contrast and adjust the histogram to make the prominences pop out on the right hand side. I really remember how excited I was still to this day. And the focal length, it's really important to know the focal length of your scope and also the sensor size. On this image, this is some screenshots I did with Sky Safari on my iPad, and you can see the differences using the same camera, but different focal lengths. You can see how on the higher focal length, you have a closer image of the sun. So this would be good on the right-hand side on the 9.25-inch SCT. You can see the 174 camera, you're going to be getting some nice sunspot resolution. Whereas on the left side with a Lunt 80mm refractor, it's at a 525mm focal length. That's going to be perfect for full disk images. And that's what I do with the ASI174 when I want a nice full disk image of the sun. And then, like I said before, camera sensor size is also critical for solar imaging. The larger DSLRs or the full frame DSLRs, you're going to be more for full disk images of the sun. And that way you can get a nice white light full disk image. But if you're going to if you're going to go for the sunspots or really zoomed in view, I would also get a dedicated Astro camera. And we'll talk about some of the Astro cameras. This screenshot from my iPad on using Sky Safari shows the same scope. This is a Lunt 152 refractor with a 840mm focal length, but I inputted the 3 solar cameras that I use. I use a ZWO ASI174mm, which has the largest sensor, and you can see it gives a nice full disk image. And then I go down to the ASI174, which is the middle, and then the ASI178, which has a nice smaller view and a high frame rate. And these are some of the different DSLRs and also the astronomy dedicated cameras that are out there on the market that are popular. I just have some of the sensor sizes that you can see, and I put the price tags on the cameras too. Because people ask me, well, what camera should I get? And I always tell them to go with either the 174 or the 178, depending on what scope you're using it on. And I'll show you my formula that I use to calculate that too. And then when you're using a DSLR, these are my recommended full frame or for the full disc images, to the recommended focal lengths to use. So with a full frame camera, you're going to want a minimum of 634 millimeters and a maximum of 1268 millimeter focal length scope or lens. And then on the Nikon APS-C, 415 to 830 millimeter focal length. And then Canon APS-C, you can see 391 millimeters to 782 millimeters. And these recommendations are for full disc images. And this is what I was giving out around the time of the last eclipse, just so people would know what size scope they would want, because you don't want a short focal length with a full frame camera, and then you're just going to be out there just imaging the sun, but the sun's going to be such a small scale. And this is my pixel size formula that I use. And in solar imaging, it's better to be oversampled. It's not like nighttime imaging where you want that perfect, you don't want to be undersampled and you don't want to be oversampled. You want it to be just perfect. But with solar imaging, it's better to be oversampled. So I use the focal ratio divided by 5, and that tells me the approximate camera pixel size that I want. So I threw 2 of the examples that I use here. So I have my 152 millimeter scope with the which is f5.9, and then the Daystar Quark with the built-in 4.2x Barlow. When I do the math, it tells me that the optimal pixel size of the camera should be at least 4,000 or 4.956 microns. And then with my 60 millimeter Lunt solar scope at f8.3, I run the math, and it's telling me that the optimal pixel size of the camera should be at least 1.66 microns. So this is where I carry it over, and I like to use the Lunt 174 and the ZWO ASI174 and the ZWO ASI178 for my imaging. And then we get into the monochrome versus color. And obviously in solar imaging, when you're imaging in narrow band, monochrome is always going to be better because it's going to collect more photons and it'll provide a more detailed image. Whereas you have your color cameras or your OSC one-shot color cameras, which have the RGB Bayer matrix, and you're going to have photons that are going to be rejected, and the detail's going to be lost. So that's why I always recommend to people to use monochrome cameras. By chance, if you are using a DSLR channel or camera, you can always just use that red channel when you're imaging hydrogen alpha and get rid of the green and the blue, and then bring that into Photoshop, process it, and apply false color to it. And that'll give you the most detail for a DSLR or an OSC camera. And then when you're looking at your DSLR camera and you're using the ISO settings, the greater the ISO, the brighter your image is going to be. And also on that same note, the greater your ISO, there's going to be more noise in your image. So the recommended ISO speeds out there are 100 for the solar scopes that are from f3 to f5.6, ISO 200 for f5.6 to f11, and 400 for f11 or more. And I always use ISO 200 on my Canon 450D and my Canon T5i. And then shutter speed, that's a control on the DSLRs for your exposure. 1/2000th of a shutter speed is going to be quick, letting in less light, and you're going to be underexposing your image. Whereas on the other side, a 3-second exposure is going to be a lot longer, and it's going to allow more light, and it's going to overexpose your image. And I have some examples here that I did. So as you can see, these are different exposures, and you can see on the left, the 1/30th of a second, that's overexposed, whereas the 1/2000th of a second is way underexposed. So I would pick a 1/125th second exposure, which is, in my opinion, just perfect. It's not overexposed and it's not underexposed. And then focusing with a DSLR, it's a little bit more tricky because you have the focus, it's more of a helical focus on the lens. So what I do is I go into the live view and I zoom right into the sun. I'll zoom right into a sunspot, or if there's no sunspots, I'll zoom into the limb, and I'll very gently use my hand to twist the focus and get it in view while it's zoomed in on the live view. Then intervalometer, because if you're using a DSLR, you're going to want to use some kind of trigger to trigger your exposure, because if you try to push the button, it's going to jump and it's going to blur your image, kind of like night's deep space imaging on that note. There's also specialized scripted software such as Eclipse Orchestrator or Backyard EOS that I used for taking my first solar images. And this is going to allow you the hands-off capture so you don't shake the camera. Then this is really popular with the kids. It's the cell phone cameras. They like to, and I have different adapters I bring to outreach so the kids can put their camera in. I use the Celestron, that NextYZ adapter, and it just goes right on the eyepiece, and it'll fit any of today's smartphones, and it's a hit with the kids. That way they can bring home an image of the sun that they're proud of. So here we have a hedgerow prominence. And this is at one of the outreach events I did. Actually, I think this was the Adirondack Sky Center's Astro Imaging Conference a while back. And we had our cameras out there, and this kid had a cell phone camera that he used on the Lunt 152. And then you also have the high-speed CCD and CMOS cameras. And unlike the DSLR cameras, the Astro dedicated cameras must be used and controlled with a laptop. So this is a little bit more where you're going to be tied down to a laptop, but you're going to get much better results with this. They're more sensitive, they have lower noise, they have higher frame rates, and instead of the ISO and shutter speed, they're controlled by gain and exposure. And gain amplifies the signal off the sensor, which will increase or decrease the brightness. And a lot of people think, hey, I'm imaging the sun, so maybe I should get a cooled version of the camera. But when you're imaging the sun and it's a fast exposure, cooling doesn't matter. And it doesn't, your camera is not going to overheat. I've had cameras out underneath the sunlight for 8 hours at a time, and the camera doesn't even come close to overheating. So when I tell people who are looking for a solar camera, I tell them don't even bother with the cooling. It's just going to be an extra cost unless you're going to use that camera also for deep space, longer exposures. Then you would want to get the tech cooler included. And then for why I like the high frame rate is because for narrowband imaging, the goal is to freeze the seeing and capture as much detail as you can in the shortest amount of time. And to do this, you must have a fast camera with good resolution to capture as many frames as possible. And then once we process them, we're going to stack the images together and combine the images to pull out the detail and sharpen the image in post-processing, which I'm going to show you at the end of this presentation. My first Astro dedicated camera after I was using my Canon 450D was the Point Grey Chameleon. This was a USB 2 camera. At the time, this was one of the go-to cameras. It's a great camera. I still use it, still have it. It's just a slower frame rate, and you can see it's 18 frames per second, and that's extremely slow for what I want to do with my imaging. And then I currently use, my favorite camera is the ASI174, and that's at full resolution. I can get 128 frames per second. But if I'm using a region of interest, or if I go down to 640 by 480, I can get upwards of, I mean, it says 397, but realistically it's about 200 frames per second. And it's 2.3 megapixels, and it has a Sony CMOS sensor, and it's adjustable via the laptop, but it's the high frame rate, which I like. And then people ask me what type of file format should I capture. I always recommend, because you can capture with basically in RAW format or JPEG format. But with the Astro dedicated cameras, I like to do the 14-bit format, and I like to capture in serial format. When I've imaged with AVI format on the Astro dedicated cameras to get my high frame rate, if one of those files, or if one of the frames skips, that whole AVI file is corrupted. Whereas if it skips on a serial file, I still have usable data. So that's why I always use the serial format. And also you can see the 14-bit, the shades of gray, and shades are 0 to 16,383, which is significantly much greater dynamic range than the 12-bit format, which is 0 to 4,096. And on that same note, the higher the bit format, the slower your camera speed's going to be, and the more storage you're going to need. So when I go out and image at 14-bit format, it's very common for me to shoot a 4,000 frame video or serial file, and it's going to take up about 3 or 4 gigabytes of space. It's extremely large. And during the meeting earlier, we were talking about, someone was talking about Mars and the seeing, and seeing applies just to solar imaging as it does with planetary imaging. I live under the jet stream, so I'm always fighting the upper turbulence in the atmosphere, and the seeing's dependent on the atmosphere stability, the wind, temperature, moisture, and the high level clouds. For me, where I am, I find the best time to image the sun is in the early morning between 9 and 11 a.m. Or if I miss the early morning and the seeing starts to go lousy, I'll go back out in the late afternoon between 3 and 4 p.m. and I find the seeing is a lot more stable. And the larger aperture scopes suffer a lot more from the seeing than the smaller aperture scopes. So there's some times where I'll bring the Lunt 152 out and I'll look at the sun and I can see, oh, it's boiling over. It doesn't look great at the higher focal length. So I'll set up my Lunt to 80mm, and the Lunt 80mm is much more, it handles the seeing much better, and I can get some nice images with it. And here you can see, I always monitor the jet stream map, and this is from weatherstreet.com. And it's nice, you can see when the jet stream's south of us, or if it's hooking and it's north of us. I like the jet stream to be north of me, because then I have the high pressures usually, and it makes it a lot more stable for me. And then I also look at the pressure maps. And obviously, if you have a high pressure sitting over you, it's going to bring that stable seeing, as opposed to a low pressure coming in, bringing some storms, bringing some wind, and some unsteady seeing conditions. And there's also the clear sky chart. I really don't use this that much, but it is an option to use. My favorite app is going to be the Astrospheric app. I don't know if some of your club members have used this. It's a free app, and it shows everything on it. When we had the fires out west, it has an overlay for smoke, and I could see, oh, there's still smoke overhead, and it's gonna not be a good day to image the sun. And it also has the different map layers. It has transparency, seeing, wind, temperature, the dew points available. It has the satellite imagery, radar, and the sunset, sunrise times, which is nice. And then when I'm using the Lunt 152, I'll use a solar scintillation monitor, and it's a little device that goes on the scope, and it actually looks at the seeing. So when the seeing is high enough or low enough where the seeing is stable, it will automatically trigger my capture, and it allows me to image the sun with sharp resolution when the seeing is the best. And here you can see this is the solar scintillation monitor hooked up on my scope on the 152. I have the little diode up front, and then it comes back to a box. And then I also have it available. So this could be a standalone unit, or it could hook up to my laptop and it triggers the capture and fire capture software, which I'll talk about the image capture software shortly. But also it has a readout of the seeing, just to give you an idea of how the seeing is. And other fun things that I like to do with the sun is I like to image transits. So whether it be, I mean, we're not due for another planetary transit until November of 2032. But in the meantime, the International Space Station is a great target to go out and image as it transits the sun or transits the moon. I have a great time with that. You can also capture birds, capture lucky shots with airplanes going in front of the sun. And obviously the moon, when the moon transits, we have the solar eclipse, and our great North American eclipse is April 8th of 2024. And that's going to be passing right over my house in the Adirondacks, but I'm just worried about the clouds or the seeing that day. So I may look for some other options, or I know Tupper Lake at the Adirondack Sky Center, I bet we're going to do an event there. So I'll probably be out there for the solar eclipse with the big solar scopes. And then to monitor for upcoming solar transits, you can use calsky.com, CALSKY.com. You enter your location, your latitude and longitude, and it will alert you to satellites and the ISS transits across the sun. And it's very accurate. I'm actually really impressed with how precise they are to do that. And I like to image the transits in calcium K. On the left, you can see the ISS transit with a nice sunspot. And then on the right, this is the eclipse, and that's also in calcium K. And then capturing the image, I like to use Fire Capture. It's a free software. Previously, I've used Backyard EOS with my DSLR. I've also used Janica Astro, and then ASI Cap if you're using a ZWO camera is also free. But my go-to software is Fire Capture. It has a lot of options, and it gives me great results. Some other imagers use SharpCap, but that costs some money. But SharpCap, there's a lot more features with it, and it's worth the money if you're looking to go with a paid product. So what I do with that, I focus on the solar disk feature, and then I'll capture about 2,000 to 4,000 images using the 16-bit mode and recording to a serial file. So some of these cameras, they don't support 16-bit, so it'll bring it down to 14 bits. But as long as you have it set to 16-bit, it'll record in the 14-bit mode, as opposed to having it set to 8-bit and losing out on the dynamic range of your image. And then I adjust the gain and exposure. So the histogram's around 80%, 80 to 90%. You don't want it overexposed, so you clip your data, and you don't want it underexposed to lose the data. And on that note about gain and exposure, I like to try to balance it out so I get my higher frame rate. So if my exposure is too high, it's going to drop my frame rate. So I like to lower my exposure and increase my gain just enough to bring that frame rate right up. And I like to get around 100, 150 frames per second when I image the sun, just because I'm ahead of the seeing, and I'm not fighting the seeing, and my objects aren't blurring if it's too long of an exposure. And if I'm doing a prominence and a disk image together, I'll use two exposures and merge them together, because obviously when I'm imaging a prominence, the sun is going to be, the sun surface details going to be overexposed. So I take two images and then I compose them together. So the prominence is going to be a higher exposed image, or you can boost up the gain to take your prominence, and then I'll decrease it to get a full disk image, and then I merge them together in Photoshop and combine them into one image. And then this is Fire Capture software. You can see my histogram's at 70% in the bottom, so I'd bump it up to about 80%. And then I have this limited to 1,000 frames in this example, and then you just hit record. And here's another example in Fire Capture. And you can see the spicule. This is hydrogen alpha wavelength. You can see the spicules on the limb, a nice little active region. on the disk. And then this is Janica Astro. This is a paid product that you can use. And this is with my point gray Chameleon, a full disk image using my Lunt LS60 scope. And then this is ASI cap. So as you can see, the different imaging software, they're all basically the same. They have the histograms, they have the adjustable exposure and the adjustable gain. They're all going to be similar. And I just prefer the fire capture for it because I think it's the simplest format and it's what I'm used to using. And then flat fields, just like nighttime imaging, you're going to want to take flats depending on what you're doing. The sun's extremely bright, so all your dust bunnies and the uneven fields are going to be very visible. You'll also have some artifacts such as Newton's rings, and I'll show you some examples of that. So what I like to do is defocus the image for my flats. And I know with nighttime imaging, when you take a flat, you don't want to touch the focus, but with solar imaging, it's a whole different game. So you want to, what I do is I back out the focus and I blur the image, and then I'll take 1,000 frames and then I'll load that into fire capture as my flat field. And you'll have a nice image which will show the dust bunnies and artifacts and the Newton's rings. And then for the full disk images, what I use is a produce bag from the grocery store, and I'll put that over the front aperture, and then I'll increase the gain or exposure to match the histogram or be approximate to what I'm imaging as the full disk image, just so I have the same kind of sort of disk. So when I apply that to fire capture, it's going to cancel out any of the uneven brightness or the Newton's rings. So here you can see this is a high resolution image using a Daystar quark, and you can see there's some dust bunnies. These aren't sunspots, they're actually dust bunnies. And if I go to the next image, this is my flat, and you can see there's a little bit of Newton's rings on the right hand side and all the dust. So then now once I apply it, it gets it all gone, and you can see there's some noise, but it'll go away during processing and be pretty. But I just want to show a close-up of what the flat does for your image. And then here it is together. So above we have the image without the flats applied, and then below with the flat applied. And you can see it gets rid of the dust bunnies and the Newton's rings. And here's an example of Newton's rings. So Newton's rings are caused by tilt in your imaging system, and you can correct this. ZWO has a tilt adapter, and Daystar has a nice tilt adapter as well that you can use to take care of the Newton's rings. And then stacking. So just like the nighttime images with solar imaging, we're going to want to take numerous images, stack them together. The noise will decrease and the atmospheric disruption stabilizes. And a common misconception of this is the resolution increases. The resolution always remains the same. When I stack my solar images and planetary images, I like to use Autostakkert, which is free software. They're on Autostakkert 3 now. I still have Autostakkert 2 on my computer. And then I bring that TIFF file from the output of Autostakkert into Registax, and then I adjust the wavelets. And Registax is also a free software. And when I stack my images, I stack only 20% of the best images. And I use such a low number just because it will get rid of some of the boiled or the images that are jumping around. And it'll let you be using the higher quality images for your final image. And I actually, in Autostakkert, you can set up different percentages to see how it looks. So I'll use 10%, 20%, 40%, and 60%. And then that way I can see the differences. And if 40 or 60% looks good, depending on how the seeing is, then I'll go with the higher percentage. That way there's less noise in my final image. And this is Autostakkert. You can see on the left-hand side, it's very easy to use. It guides you right through step 1, step 2, and step 3. So step 1, you're going to open your file. Actually, step one, you're going to open your flat file, and then you're going to apply the flat. So once you have it applied, you're going to want to click Create Master Frame, and then it'll be your master flat. And then you'll go back, and then you'll load your actual solar image, and then you'll go back, and then you'll load your master flat frame. And then you can see the flat will be applied. And then if you're using a grayscale camera or a monochrome camera, make sure you go up to color and click grayscale. Sometimes if you have it set to RGB or it's not on auto detect, it will leave a funny color pattern in your final image. And then once you have your file open, then you go to analyze. It's going to analyze your image. And then the next step is going to put your alignment points in. So what I do is I automatically click place align points in the grid. And then you can also check off replace. So then say you have too small of alignment points. So if this was set at 24, it would show me I have about 8,000 alignment points. I try to use about 600 alignment points. So I adjust the size to get that. And then your next step is to go into step 3, and you can stack those images. And you can see right up here, I have 20% of the frames that I'm going to use. And I also like to automatically check sharpened, and I blend raw in for about 30%. And this will give me kind of a preview of what the image is going to look like. And then you can see on the left is the original, and then the right is stacked and adjusted with wavelets. Actually, I'm sorry, this is going to be stacked, and then this is going to be stacked with the sharpened applied in Autostakkert. I haven't adjusted the wavelets yet. So now I'm going to load Registax, and I'm going to select my image. And it's going to ask you stretch intensity levels. I always say no, because I like to process it myself. I don't want Registax to apply anything other than what I tell it to do. So I always check no. And then you're going to have the image pop up, and then I'm going to adjust the wavelets so you can see it goes from no wavelets applied to wavelets applied. And then you have a nice sharpened image. But I don't like to over sharpen it, because I like to bring it into Photoshop and adjust the sharpness in there if I need to do it fine. And then in post-processing, you can use Photoshop, which costs money, or you can use GIMP, which is free software. And they all have basically the same controls. I use the brightness and contrast, levels, curves, and then the exposure, and then I go through the final sharpness. And then the last step is, since you have a monochrome image, I use the curves to apply false color so the image is more pleasing. So here's Photoshop, and then false the color applied using curves. And you can see, so the only steps I did to process this image is I adjust the brightness and contrast, and then I applied the curves to colorize the image, and then the final image. And some other helpful software, and this goes for planetary imaging as well as solar imaging. There's PIPP. It's free software, and it'll stabilize your image, and it'll convert your image. You can go through and optimize your serial file or your AVI, so you can bring it into Autostakkert to process easier. And another helpful software is IMPGG. This is very popular over in Europe. I haven't used it too much. I just used it just to get familiar with it and see if it would give me better results, but I get just as good results using Photoshop as this software. And then another helpful resource I use is the Solar Gong. It's the website's at the bottom of the screen. It's halpha.nso.edu, and it has solar telescope and cameras set up around the world, so you can always have keep an eye on what's going on the sun. So you can see on the eastern limb here, because it's backwards. Remember, it rotates east to west. You're going to have this little sunspot region coming in. This is a live view I clipped off the Big Bear solar scopes setup, and I put it in the presentation. So you can see there's an active region rotating into view. You can see there's some nice prominences on the limb, and there's it looks like a filament on the up top. And then there's another active region in the center, lower hemisphere here. So there's a lot of activity to be out there imaging every day. And then some of the additional information out there, Jamie Jenkins has a great Observing the Sun pocket field guide. I like to bring this with me to events, just have it on hand. Sometimes they'll ask me questions that I don't know because I'm not a scientist, I'm just an enthusiast, and this is my hobby. And I like to share the sun, so I like to bring this field guide with me. And if there's something I don't know, I can reference it easily, and it has a lot of great facts in it. There's also some great information out there. Stephen Ramsden, he runs Charlie Bates Solar Astronomy Project and also Sunlit Earth. He has some great forums, great images, and it's a wealth of knowledge on solarastronomy.org. There's also Solar Activity, which is a Facebook group, and there's a lot of solar enthusiasts, and that's run by Pam Shivak, and that has some great information on there as well too. So I highly recommend joining the groups. If you're on Facebook, or if you're not on Facebook, check out the website, solarastronomy.org or solarchatforum.com, and there's some great information on there as well. Then here's my information. If you ever have any questions, feel free to reach out to me. I try to post on my astronorth.com website. There's also a blog on there that I like to share images. And I'm also active on social media, mainly on Facebook. But if you ever have any questions, feel free to send me an email and I'll try to help you out or answer your questions or give you some tips, because I've been doing this for a while and I've made mistakes and I've gone through different gear. So I like to share my knowledge based on my errors and my mistakes I've made down the road. And you can see every step of the way, I involve my son, and my son has a blast with it. And it's a great family hobby. So on that note, thank you very much for having me. This is the end of the presentation, and it was great to be with you guys this evening.
Thank you so much, Tim. That was really informative and very interesting. I learned a lot.
Yes, indeed. Thanks very much. Are you willing to take questions?
Yes, absolutely.
Because I've got one.
Okay.
You had mentioned the tilt versus the pressure tuning systems. I've got a little Lunt, and I believe that it has a tilt tuning. It's a little tiny knob up on the front that actually tilts the very first bit of optics that comes in, right? Well, what's that actually doing? And what's the difference between the tilt and the pressure?
So it's just different ways that you're coming on band on the hydrogen alpha. Because it's very fine, you can actually tilt tune it just to fine tune the wavelength that you're looking at. Whereas a pressure tuner uses the pressure from the air. So when you turn that pressure tune knob, it's changing the pressure, and it's basically applying the tilt with pressure. Yep.
Is there anything specific that you're looking for? I have noticed that I can get the prominences in, but is there something else that I should be looking at? I'm very new at observing the sun, so.
Yeah, so I usually what I do, because I did have a tilt tune blunt 60, so I'm familiar with how those work. So what I would do, and also the Coronado is a tilt tuned as well. So what I do is I kind of rack the tilt back and forth to look at the surface features. So the prominences are one thing I look at, but more often I look for filaments on the sun or some of the hydrogen alpha features that once it's in tune, you're going to really see. And a lot of people, when they first get their solar scopes, all they see is a red ball of light. So it takes a little bit of getting your eyes used to the hydrogen alpha wavelength and training them. Because I can't tell you how many times I set up in a field and I have a bunch of kids that come to the scope and I ask them, oh, what do you see? And they say, I see nothing. I just see a red ball. And
Yeah.
it's not very entertaining to them. But then I tell them, okay, look back at it, give it 2 minutes, keep the hood over you, and tell me what you see. And then after the 2 minutes, after time goes by, they're like, oh my gosh, I can see that on the sun. Now I'm starting to see the details. So I try to, when I'm tilt tuning or pressure tuning, I look for the surface details and I'll rack it back and forth just to see what brings out the most details. And some people even like to image off band because sometimes if you're looking at the upper chromosphere, there could be some sunspots that are on the photosphere and they like to be off band to image them or view them. So it is valuable to rack the tuning mechanism around just to see what you can image and what you can view. But if you're doing primarily viewing, there's nothing wrong with a tilt tune. Even some of the imagers, I've seen some great images from the tilt tuned the Lunt scopes, and they use flats to compensate for the gradients, and they also produce great images. So I hope I'm not stressing anything. Pressure tuning versus tilt tuning. Pressure tunes better because that's not always the case. It always comes down to how skilled are you to tune it, and that's sometimes why a lot of people prefer the Daystar setups, because all you do is power it on and you wait 15 minutes and you're on band, and it's very consistent. So there's no tuning involved.
Cool. Thanks.
Yeah.
Hey, Tim, this is Don. A very delightful talk. Thanks for inviting me. I got a question. Can you talk about the difference between using a primary telescope that's based on mirrors versus one that's based on lenses?
Okay, so I used a 8-inch Newtonian, and I used that with a white light filter. And I also, my SCT scope, which uses the mirror and it also has the corrector plate, which some would consider a lens. You can use either one. Just with the larger mirrors, you're going to want to make sure that you have an energy rejection filter on the SCT if you're imaging in hydrogen alpha. But I've seen some great high resolution images with a higher focal length mirrored scopes like the SCTs. The Newtonian, I had nice views on that. And I mean, I don't see a difference between them, but I know most people use refractors, and it's easier and less expensive to use for your, if you put a quark on it or you put a Daystar filter on it. But I also like my solar dedicated refractors just because the compact size, I can bring it to the park with me or put it in a bag or a backpack.
Great. Thanks, Tim.
Yeah. Any more questions?
Well, to follow up on that one, I saw a really brilliant design of a reflector telescope. I think it was a 6-inch, where the solar filter was just a white light, but the solar filter was a a metal coated piece of glass, but it was used halfway up the focal length, and it was angled at 4 degrees so that the reflection came back down, and you put the focuser next to the primary, So what you end up with is an unobstructed Newtonian using the solar filter as the secondary. And it was really
Wow,
brilliant and extremely high contrast. It was sharp. It was impressive.
yeah, yeah. And with my Lunt 152, I would like to, instead of using my Baader, my 2-inch Baader to filter attached to the diagonal, I would like to at some point get an external rejection filter, energy rejection filter, just so I don't have the turbulence inside the tube. Way it keeps it outside. So, because I suspect the images would even be more sharp that way. So that is a brilliant design, though, the way you just described.
Any other questions for TJ?
I have one question. It's not a technical question. Am I on?
Yeah.
Yes, I hear you.
Okay. Do you ever get involved, or does your hobby enable one to predict coronal mass ejections?
So I have not got into that, but I have observed active regions and flares that do trigger like the northern lights or the streams, the winds. So if I see one that is kind of earth oriented, you can kind of predict that, hey, we're going to have some northern lights coming, or get ready for the northern lights. So it's pretty wild to be able to see that. But my favorite is that coronal loop, which was on the eastern limb of the sun. And that was pretty wild to view and witness. And since 2013, I've only seen 2. So I know they're pretty rare.
Yeah.
TJ, you mentioned NEAF a couple of times, and I was at the one last year where I don't remember the solar booth, but one of the solar booths was building something extremely large. Did you happen to see that? And do you know what I'm talking about by any chance?
So I'm trying to think, because I know Randy Shivak had his huge refractor.
No,
and then
this was, they were piecing something together. They had like a bit of a lens and then braces that came back, and then a bit, and this wasn't Randy. I worked with Randy a little bit too. This is actually in the inside the display area, and they were putting, the thing was about 5 or 6 feet long, and probably maybe, I don't know, 14 to 18 inches at its largest. And I never
was that at the Lunt booth?
I think it was at Lunt, but I'm not 100%
so
sure.
Lunt, yeah, so Lunt had, I remember now what you're talking about, and I thought you were referring to out on the solar field.
No,
but Lunt had at their booth one of their new solar dedicated scopes, and it was, from what I recall, I want to say it was a truss design, and it was massive.
Yeah, it was
so
monstrous.
I haven't. Yes. Yep. I remember.
So that was basically just several image pieces of a solar scope then? Wow.
Yes. Yeah. That's one of their massive scopes. And I'd have to go on their website just to see an update on that project.
Yeah. I wanted to find out what that was and never did, darn it.
Yeah.
Marvelous. Any other questions for TJ? All right. Well, thank you very, very much, sir. That was absolutely marvelous.
Oh, thank you. Thank you.
Yeah, I've enjoyed looking at the sun relatively recently, and it's always been fun.
Yeah, and I think our solar activity is going to really start to pick up in the next several months, and as we go back into solar maximum. So I think our hobby of solar imaging and solar viewing is going to really pick up. So if anybody's on the fence of buying a solar scope, now's the time to get into it and get it before they're sold out.
Yeah, really. I'll point out right now that after everything is said and done, some of us will hang out here. However, many people would like to stick around and just chat about things. whether it be related to our presentation or anything else, you're perfectly welcome. Normal days, we'd all go out to a diner and have some tea and cookies, but we're stuck at home for that. So appreciate it. TJ, it's been marvelous. Thank you very much, sir. I'm looking forward to seeing some of your stuff. I wrote down a lot of your websites, and I will be on those soon myself.
Great. Thank you.
Thanks again, Tim. That was awesome. Very awesome.
Yeah.